It's my pleasure to give this talk here, and Herman instructed us to prepare the first lecture in very general terms, and the second lecture will be more specialized and going deeper into some recent results. Then also I will use a few slides concerning Alexei Abrikosov. So Andrei, my apologies if these slides are also on your list, okay? I didn't know about this, but all right. So then this work has been done in collaboration with many people. So, and now I will start with this very general introduction. So basically, superconductors, superfluids, and Bose-Einstein condensates give us a beautiful example of quantum condensates. And in these materials, quantum condensates are formed in the framework of the whole sample itself. So if you have a superconductor with 1 meter size, 10 kilometers, or 100 kilometers, you still have to use single so-called order parameter wave function to describe the condensate of Cooper pairs. So this is truly remarkable example of quantum phenomena on a macroscopic length scale. Very much so about, for example, if you have superfluid helium, and if you have a big vessel, then it's also described the whole stuff with one wave function. While in courses of quantum mechanics, you learn normally that if you go quantum and you have some quantum equations, then this is applicable for electrons, for atoms, and other angstrom size and nanometer size objects. But that's not correct, actually. All right, and I will not be talking about superfluids and condensates, but we'll focus on superconductors. So superconductivity was discovered by this famous person, Heikki Kamerlingh-Onnes, and you can read very fascinating details of this great discovery in a recent book written by Dirk van Delft, who is working in Museum Burghaven at Leiden University in the Netherlands. And he gave a very interesting lecture at our Vortex 7 conference in Rhodes in 2011. And there it was exactly 100 years since the discovery of superconductivity. And next to it, you see also one of the most expensive superconducting tools. I'm not counting here superconducting magnets of huge accelerators. This is by far the most expensive stuff. But this unit is a magnetic resonance imaging. And if your doctor gives you advice to go there, then you should be prepared to sit in this locked space for quite some time. Tend to lie in this locked space, and if you're claustrophobic, better not to go there. And it's also very noisy when you sit inside. All right, but it's using superconducting coil, and this is one of the biggest examples of application of superconducting materials. And there was a big celebration in Leiden on that occasion in April 2011, and I had the honor to be invited to that. And then this milestone of IEEE in electrical engineering and computing was revealed concerning discovery of superconductivity on 8th of April 1911 in this building. Professor Heikki Kamerlingh-Onnes and his collaborators, Cornelis Dorsman, Gerrit Jan Flim, and Gilles Holst discovered superconductivity. Note here already collaborators. So I will come to this point a little bit later on. So they observed that the resistance of mercury approached practically zero at its temperature, as its temperature was lowered to 3 Kelvin. Today, superconductivity makes many electrical technologies possible, including magnetic resonance imaging, MRI, and high-energy particle acceleration. So, biggest applications are mentioned here, but first back to the discovery itself. So, like many other great discoveries, this discovery was pure accidental. So this is the building where this discovery was made in Leiden. So quite old photo. And this is Kamerlingh-Onnes himself. And the drive was to answer this open question: what would happen to the resistance of a metal as its temperature approaches absolute zero? And this had some practical importance as well. Namely, can metal wires still be used as thermometers at very low temperatures because of these heating problems? And at that time, there were two theoretical predictions concerning behavior of metallic resistance at low temperatures, two rivaling theories. The first one was formulated by Lord Kelvin. He suggested that since at those temperatures it will be extremely cold for electrons as well, these electrons would prefer to freeze, and no mobility of these frozen electrons is possible, and therefore resistance should go up to infinity. On the other hand, Paul Drude argued that this electron gas in a metal, so you have collisions, and these collisions gradually will be frozen out, and therefore resistance should gradually approach zero. So two scenarios: one, resistance shoots up to the sky; another one, resistance gradually, asymptotically, is approaching zero. And then real measurements, as I told you, discovery was made by accident. So accidentally, nobody wanted to see this, but they wanted to see either this or that. But what happened is exactly the opposite. Nobody expected that. And there was this very impressive jump. So the measurements were done by using as a voltmeter so-called ballistic galvanometer. This stuff is extremely sensitive, and basically when a signal is registered, then you have a very big swing of actually this reflected light with the mirror, and then the feedback system keeps it in order, etc. But basically you can see this big swing if this happens. And they saw it actually. And first explanation was, guys, we have somewhere a short circuit. So this is typical for measuring systems, something goes wrong. And then everything was checked, but before doing that, they said, okay, let's try to repeat it. So they stopped pumping, so they were pumping helium in order to obtain lower temperatures than this temperature, boiling temperature of helium. And then suddenly, while sitting and doing nothing, nobody touched any single button. And the cryostat was being warmed up slowly, and then they saw whoops again. So then they realized that they discovered something reproducible, and that was a real discovery of Sieve conductivity. And all this story is written by Camerlin Connors himself in the book of measurements, and he had a very lousy handwriting. So these documents are kept in special museum, but any of you, if you go there and try to read what the guy wrote, impossible. And then one famous professor in the Netherlands and in our community, Peter Kess, who's been studying vortex physics, he sort of dedicated a lot of his personal time to learn first reading simple text by this crazy handwriting. And then he was able to read and to decipher this. And then Peter actually extracted back this date of the discovery of Sieve conductivity. No, it was later on, this stuff. Yeah, so this October 1911. And then, so that's how it happened. And then again, about publishing these results. So you see already on the plaque, there were the names of these gentlemen. But on the publication, there was only the name of the initiator of the whole project and director and big boss, Heike Camerlin Connors. But what he did, he was directed, took the initiative to the mercury measurements. Gerrit Jan Flim, chief technician, so he had to build up from scratch a rather unique cryogenic laboratory, responsible together with Camerlin Connors for the cryogenic apparatus. Cornelis Dorsman, assistant, handled the gas thermometer for temperature measurements. Jill Holst, assistant, measured the resistance of the mercury using a Wheatstone bridge and the mirror galvanometer in room 1. he noticed a sudden swing of galvanometer. Short circuit? No. So basically, the guy who discovered with his eye this swing was this guy. And then Oskar Kesselring, master glass blower. So everything was made all Kreisstadt from glass. And of course, in modern conditions, all of them would have been on the author list of the manuscript to be submitted to Nature, right?
And no Nobel Prize.
And no Nobel Prize, okay. So, and the only place what could be discussed for Heike Kamerlingh-Onnes with those descriptions could be first or last place, right? Like we know. But nothing has happened. Single author of all superconductivity publications, all, not only the first one, is due to Heike Kamerlingh-Onnes. There was, however, acknowledgement by him. Of course, he valued very much help of these really professional guys, Holst, Dorsman, Flims, and Kesselring. Okay, so there was this, another story is actually how to get sufficient amount of helium gas to make these experiments. So these days, you go to the lab. If you are involved in low temperature measurements, you order DUR, 40 liters of liquid helium, 100 liters or 200 liters, and you just spend it like that, although it's quite expensive, right? But this discovery was made with a few cubic centimeters of liquid helium. A few cubic centimeters. So, and the big challenge was to find the gas. Where to find gas? Now we know that some deposits of natural gas contain, as a sort of side product, also helium. And some countries are lucky that in some deposits of gas, the fraction of helium is quite high. So, and there you can get sufficient amount of helium gas for research. But actually, our Earth is losing helium permanently. Helium is floating up and goes to a bigger space, so irreversibly. So we have to be very careful with it. So, and then where to get helium for these experiments? So then he learned that in some sands, there is absorbed helium. And this absorbed helium can be degassed from the sand, and that's how they collected a few liters, maybe some tens of liters, not more, of gas, and purified it. And finally, they started doing these experiments, and finally they discovered this superconductivity, and then eventually Kamerlingh-Onnes has got Nobel Prize. But again, a simple question, for what? For discovery of superconductivity? No, for liquefying helium. And of course, liquid helium made possible to make this great discovery. So there was also a big celebration in this 2011, and they invited scientists, but also some relatives of this Kamerlingh-Onnes tree. And there I met this lady, so Catherine Kamerlingh-Onnes, and then a very interesting and intelligent lady, and she told us about some old documents of the family. And then Peter Kess told me that, look, the tree of Kamerlingh-Onnes, the branch related to him, is dying out because she will be the last offspring of that, direct offspring. Indirect, there are many, but direct offspring, and she doesn't have kids.
She's a granddaughter or granddaughter?
Granddaughter. Yeah. But it will be over anyway, so in that sense, but not the discovery, you know. So. All right, so now we go to superconductivity and to the next milestone. So basically it was 1911, and since then there was a sort of gold rush to find different superconducting materials. And coming back to this question, what would be behavior of resistance going up, asymptotically going down to zero? The answer given by nature is it will sharply go down to zero, and that was discovery of superconductivity. It's very instructive. So it appeared where nobody expected it to appear. Okay.
But yeah. Are you sure that he did not take part in this dispute? I mean,
in which?
Dispute between Kelvin,
no.
between Drude?
No. He's pure experimentalist. And he said, okay, I'm the only guy in the world who has this possibility to do it experimentally. And experiment is always giving a definite answer which theory is correct. And he knew it very well.
There were two talks. First, 25th of April, because he discovered 8th of April.
Yes.
25th in Royal Dutch Society, he presented the first talk when he told, yes, resistance go to 0. But then was another talk.
Yeah, but that's exactly what, very interesting issue, what is 0?
Exactly.
That is what is 0. So if you want, yeah. So less than this. Yes.
1,000 times below the
Exactly. You see this 10 minus 4 from that. So, and that was a discussion, because in physics, in mathematics, 0 exists. In physics, 0 doesn't exist. So, yeah, it may be small, much smaller, even much smaller, etc. So
in fairness to Dewar,
yeah.
In fairness to Dewar, he wasn't the only one, because they were racing Dewar.
Yes. But I'm not talking about all these, let's say, possible.
The only one who could measure. Dewar was racing to liquefy helium.
No,
Dewar
more.
invented the method.
Yes.
He was trying to liquefy it.
Okay, guys, who is giving the talk? Sorry. Please stand up. Okay.
Happily, I can give it as accurately.
All right, no problem. It's good for discussion, your question. We will come back to that. Don't worry. Okay, so this lady. So now we are coming to another issue. So what to do with vortices and superconductors? And then soon after discovery, actually, theorists started to realize that in order to have a sort of condensed quantum state, you need electrons to pair. And then you have bosons. And then, basically, in that sense, superconductivity becomes a bit similar to superfluidity of helium. Bose-Einstein condensates at that time didn't appear yet, of course. So, and vortices were already recognized, since here it's been already discussed many times. What are the links of these great discoveries to decisions of Nobel Prize Committee? So that was done in 2003. Nobel Prize was given for pioneering contributions to the theory of superconductors and superfluids. And it was given to 3 gentlemen: Abrikosov, 1/3 of the prize, Ginzburg, also 1/3 of the prize, and Leggett, 1/3 of the prize. And this was, like it's been mentioned here also before, Nobel Committee has sometimes people coming from previous decisions. So for superfluidity of helium-3, Tony Leggett was the 4th person. And it's impossible to give to 4 persons Nobel Prize, 3 is maximum. So, and then the decision was made that next suitable subject, so this person should be added. And this was quite suitable in this case, I suppose. So, and then this is the moment of truth for these people. So Abrikosov has got this Nobel Prize, then Ginzburg, and then Tony Leggett. And if I compare how they bow, then I know immediately who is the king, right? And who is the Nobel Prize winner. And then I can compare who is from the 3 guys has the highest self-respect. So let's make it back. Wow. So clearly Ginzburg. Okay. And you can now on the website, you can read all Nobel Prize speeches of the laureates. And in his speech, Ginzburg started by a very remarkable sentence saying, "I'm thankful to honorable members of Nobel Prize Committee that they made this important decision before I had died." Because again, it's very well known that Nobel Prize cannot be given to people who are already dead. So. And then, all right, so this is a short CV, like we say, of Alexei Abrikosov. So, and then he started his career as scientist in Institute for Physical Problems. And he's graduated from physics department of Moscow State University. So I had the honor also to have been graduated from that. And then he's made prediction of new type of superconductivity because we have bosons. responsible for condensation and for superconducting state, and bosons are singlets, mostly. Triplet superconductivity is not yet established. And actually, if you then apply magnetic field, so then the second spin is polarized and you destroy superconductivity. And if you take superconducting wire to ignore demagnetizing effects and apply magnetic field like that, then superconductivity is killed abruptly. So you have either superconducting state or normal state. So if you have, let's say, film or slab or something like that, then you have demagnetizing fields, and then you have intermediate state where you have a mixture of superconducting normal domains, superconducting normal. And actually, Abrikosov came up with the idea that besides this so-called type 1 superconductivity, there is another sort of superconductivity, which is so-called type 2 superconductivity. And for that, he's got his Nobel Prize. In '91, he moved from Russia to Argonne, where I suppose Valery has got a lot of discussions with him. And he's famous, of course, for his work not only for superconductivity, but for some other previous work concerning, for example, heavy fermions and condolences. There is Abrikosov-Sulu resonance there. And finally, in 2003, he's got his Nobel Prize. And also, with the help of our big friend Sasha Buzdin, who is a professor in Bordeaux, you can find also that Abrikosov was awarded with honorable citizenship of Saint-Emilion, France. Saint-Emilion is Bordeaux area for one of the best red wines in the world. All right, so that's actually the discovery itself. And you see that it looks simple to detect it experimentally by measuring resistance as a function of temperature. And then very interesting experiments were performed here to detect actually what is here still the resistance. And then the best way is to inject supercurrent in a superconducting ring and then to measure it constantly as a function of time, hoping that it will start sooner or later to decay. So this experiment was done in the UK for several years, and then it was stopped because of the strike of transport workers. They couldn't deliver liquid helium, so they couldn't cool it down. So they estimated from this a few years the resolution of the best voltmeter they used, and then they came that actually this decay time, if superconducting current in a superconducting ring decays, so it's comparable with the age of our universe, something like that. So it's really quantum state which is not dissipating, non-dissipating. All right, so, and Ginzburg came up in early 50s with the so-called Ginzburg-Landau equations, first for the order parameter and second for current. Second equation is just quantum mechanical equation for current if you have wave function, and the role of the wave function is taken by a so-called order parameter in case of superconductivity, but if you like more order parameter wave function, you can still say wave function, there is no problem with that. And this one is kinetic energy of your condensate, and then this is eigenvalue, and this is nonlinear term. So basically it's nonlinear quantum mechanics in its beauty. So, okay, and this is a Nobel Prize diploma to Vitaly Ginzburg. So my Swedish is 0, so those from Scandinavian countries can read it in this language, but we do understand the meaning of that, so that he suggested to describe, like we describe with wave function electrons in quantum physics, to describe macroscopic condensates of these particles. And then if we go to the same diploma given to Ginzburg, then we can recognize with some efforts that these are possibly vortices, right? So. All right, so now we are moving to the subject of vortex matter in superconductors. And first, a few general words about superconductivity in this case in bulk materials. And then basically we will see what's coming out in case of nanostructured materials. So this is an example of vortex matter which is not quantum but classical. Big hurricane, and a remarkable point is that you have a swirl of clouds here, but then you have a quiet place which is a core of the hurricane, or an eye of the hurricane. And actually we will see that similar thing will happen with a quantum condensate if it's rotated by Lorentz force in presence of magnetic field if you apply it to type 2 Sieve conductors. So and now a little bit about this vortex core problem. This is also a very interesting problem. So if you consider a circular contour inside of a Sieve conductor, then you can, in a certain simple approximation, derive that superfluid velocity should be given by this orbital quantum number and inversely proportional to the radius of this orbit. And it's clearly seen that whatever you do, as radius goes to 0, this velocity wants to diverge. And physics does not allow and does not tolerate real infinity like mathematics. So this is a second important difference of physics with respect to mathematics. No 0, no infinity. All right, so what to do with this problem? So what you can do is you can claim that in quantum matter, the only state which is allowed is L equals to 0. And this was believed till late 30s. And the first guy who questioned that was Onsager. And Onsager said, look, why do we write it like that? That basically we have to multiply it with the density of your quantum matter, square of your wave function, modulus of your wave function. And then remarkable thing may happen that if radius goes to 0, if we demand that at the same point where radius is 0, then your order parameter is also 0, then you can take finite L. And finite L means that you have vorticity in your quantum system. And that was done basically briefly before the Second World War and not very well known. But then soon after the Second World War was over, Feynman came back to these papers of Onsager, and he advertised it a lot and added a lot himself when applying this concept to superfluid helium. And then in the beginning of 50s, the transfer of the literature, so it was the time of the Cold War between the United States and at that time the Soviet Union, was very difficult, and then actually Landau and best theoreticians and experimentalists in the former Soviet Union, they didn't know about that, actually. Although they studied a lot superfluidity and also at that time superconductivity. And then what happened is what I have heard, how it happened already from Abrikosov, that in fact, so he told me in 2003 this story on the following occasion. So we organized this Vortex 3 conference. Conference site was Crete, and Abrikosov is here. So Dima Rodichev is somewhere here. I saw him here, yeah, and many others. Okay, it doesn't matter. But important point is, so we are waiting still for one guy to come because he was late. It was Helmut Brandt, who was very enthusiastic, unfortunately passed away quite early. All right, so, and then also another famous scientist was there, Andreev, and we organized a special session. It was 2003. We organized a special session which was called 40 Years of Andreev Reflection. So you might say, oh, Victor has problems with mathematics. So because you know that paper was published in 64. And if you add 2060, subtract from 2003 40 years, then you are coming back to 63. But that's exactly what he told me. So Andreev told me that he was sitting one day in underground metro in Moscow, and he came up with the idea how it should be done with the Andreev reflection, and that if you have interface between a superconductor and normal metal, if Cooper pair hits this interface, then it can be reflected back along the same trajectory as a whole, and the electron can be then injected into a superconductor in the form of Cooper pair. So everything then is conserved momentum and the charge. And then Abrikosov said, Victor, but you are very unpolite to me, he said. I said, why? What is going on? Why didn't you organize a special session, how was that, 50 years of Abrikosov Vortex? Ooh, I said,